Hey, today I'm going to show you one of the most elegant solutions to one of computer science's hardest problems, the traveling salesman problem. We'll see how the Christofides algorithm combines several concepts that we learned in class to give us a guaranteed approximate solution. So what is the TSP? The TSP is a famous optimization challenge in computer science and operations research, which asks, given a list of cities and the distance between each pair, what's the shortest possible route that visits each city exactly once and returns to the origin city? Now, this seems like a somewhat easy question. However, the TSP is considered an NP-hard problem. This means that there is no efficient polynomial time algorithm that can be found to solve the problem. However, there is an approximate solution to the TSP noted by the Christofides algorithm. So before diving into the algorithm, what do we need to know beforehand? The Christofides algorithm is a procedure that constructs a near optimal tour by combining several graph theoretic techniques, such as Hamiltonian cycles, a minimum spanning tree, Eulerian circuits, and perfect matching. We know about Hamiltonian cycles, minimum spanning trees, and Eulerian circuits. However, we don't know about perfect matching. So, what is perfect matching? We'll get to that in the last step of our algorithm. However, there are a few restrictions to the traveling salesman problem. The Christofides algorithm works on the metric TSP, where distances satisfy the triangle inequality. This means that going directly from city A to city C can never be longer than taking a detour through city B. This is realistic as it reflects actual geographical distances. So this is our six-step algorithm that we will go through, and the result is a tour that's less than or equal to 1.5 times the optimal tour. We'll go through this algorithm using the graph right here. The first step on the Christofides algorithm is finding a minimum spanning tree. We can do this using Kruskal's algorithm, where we sort edges by weight and add edges one by one if they don't create a cycle. So we select the edges AB, AE, CD, and BC. The total minimum spanning tree weight is 12. We have two vertices with odd degree, which are degree D and degree E. Step 2 is odd vertices. We go through the handshaking lemma, and you see that the sum of degrees is 8, and the number of edges is 4. 2 times 4 is 8, so the theorem holds. Additionally, there is an even number of vertices with odd degree, D and E. Step 3 is finding a perfect matching. A perfect matching is a subset of edges in a graph where every vertex is incident to exactly one edge in the subset. So in our graph, there's only one perfect matching, edge DE. As we saw from the original graph, the weight of DE is 4. We add this edge to our graph. Steps 4 and 5 involve creating a multigraph and finding a Eulerian circuit. After combining the minimum spanning tree and the matching graph, we now have a multigraph. So all the edges have an even degree. In this graph, we need to find an Eulerian circuit, which is a trail in a graph that visits every edge exactly once and ends at the same vertex where it started. As you can see, the path A to B to C to D to E traverses all edges exactly once. So this is our Eulerian circuit. The last step is shortcutting, and we need to convert this into a Hamiltonian cycle. In larger graphs, the Eulerian circuit might skip repeated edges, and as a solution, we use shortcutting. So what happens is that we take the shortcuts. We skip repeated vertexes and go directly to the next unvisited one. The triangle inequality guarantees that this shortcut won't be longer than the original path. And our final tour is A, B, C, D, E, and A, with a total length of 16. So, what is the actual proof for this algorithm? First of all, let OPT be the optimal tour cost. Now, a key insight here is that our minimum spanning tree is a lower bound on this optimal tour. This is because any tour is a cycle, and if we remove one edge from the optimal tour, we get a spanning tree. Since our MST is the minimum spanning tree, it can be heavier than this spanning tree in the optimal tour. Secondly, the matching is at most half the optimal tour cost. We can split the edges connecting these vertices into two separate colorings. One can color each alternative color red or blue. Each matching covers all odd vertices. Together, they cost at most OPT. So one of them costs at most OPT over 2. Our matching is minimum weight, so it's no heavier than this. When we combine these, our algorithm costs at most the MST plus the matching, which is at most OPT plus OPT over 2, giving us 1.5 times the original. In our example, the MST costs 12, the matching costs 4, and the total 16. If the optimal tour happened to be 12, we'd be at 16 over 12, which is 1.33. So, in conclusion, the Christofides algorithm demonstrates how we can combine different areas of graph theory to tackle hard problems. The key takeaway is that even when perfect solutions are computationally infeasible, we can still design algorithms with provable guarantees. The 3 over 2 algorithm approximation ratio was best known for the metric TSP for nearly 50 years, and this algorithm shows the power of approximation using both math and computer science. Thank you.